Okay, so welcome to lesson 2 of colligative properties. In lesson 1, I had introduced the term depression in freezing point, and I want to build on it this lesson. And we are saying that we said that freezing point of a substance will decrease once you add a given amount of a solute in a given amount of a solvent. So let's look at the terms that we are going to use here. Terms. The first term, of course, that we need to know is freezing point itself. Freezing point. We can define freezing point in a more mature way. That this is the constant temperature. This is the constant temperature at which a liquid is in equilibrium. A liquid is in equilibrium with its own solid, and they have the same vapor pressure. So, in O level, you could simply say that this is the temperature, the constant temperature at which a liquid changes to a liquid. Now, at that temperature, when the liquid is changing to a solid, it means that the solid is in equilibrium with the liquid. That's why you would say liquid in equilibrium with the solid, meaning that the two solid phases are actually there. There is a liquid, there is a solid. So they are described as being in equilibrium, and at that point they have equal vapor pressure. That's one term that we need to look at. The other term that we need to look at is depression. Depression in freezing point. What do we mean by depression in freezing point? Depression in freezing point is the decrease. This is the decrease. Sometimes people call it the lowering in freezing point, of a pure solvent when a given amount of a non-volatile solute is dissolved in it. This is the decrease. This decrease here is the difference, or the lowering, the difference between the freezing point of the pure solvent and the freezing point of the solution. This is the decrease or lowering in the freezing point of a pure solvent when a given amount of a non-volatile solute is added to it. Now, this is normally denoted by as delta T for freezing point, and it is measured in degrees Celsius. It is denoted as dT F in degrees Celsius, and is given by the formula. You say is given by the formula dt for freezing point should equal to freezing point T naught minus T, where T naught is freezing point of pure solvent, and T is freezing point, T is freezing point of the solution, i.e. that means that T naught is always greater than T. The freezing point of the solution is always lower than the freezing point of the pure solvent, because we said that the freezing point always decreases. The freezing point always decreases once a non-volatile solute is dissolved to it. So what we call depression is that difference between the freezing point of the solvent and freezing point of the solution caused when a given amount of a solute is dissolved in a given amount of a pure solvent. Very important. And this is what we call the colligative property. This is the depression in freezing point. Now, there is some more term is number 3, term number 3. I can put it here, number 3. This is called a depression in freezing point constant. Depression in freezing point constant. In freezing point constant. Also, it is called the cryoscopic constant. Now, this constant here is known for most of the pure solvents. You don't need to cram them. They are known for most of the pure solvents. And it is these constants that give us a starting point for the calculation of relative molecular mass. Otherwise, without them, we could not be able to calculate the relative molecular mass. So they are called depression in freezing point constants, or they are given the name the cryoscopic constant. But then someone could as well tell you to define what they mean. What is depression in freezing point constant? It's different from depression in freezing point. So what is depression, or what is the cryoscopic constant? This is the depression. This is the depression in freezing point of a solvent that occurs when 1 mole of a non-volatile solute, when 1 mole of a non-volatile solute is dissolved in 1,000 grams of a pure solvent. Dissolved in 1,000 grams of a pure grams of a pure solvent. 1,000 grams of a pure solvent is sometimes described as the kilogram. 1 kilogram is 1,000 grams. So we are saying this is the depression in freezing point of a solvent. That occurs when 1 mole of a non-volatile solute is dissolved in 1,000 grams of a pure solvent. And there are very many examples of these cryoscopic constants, although I'll give you some few. I'll give you some few here. I have here the solvent. I have the cryoscopic constant. Cryoscopic constant denoted as Kf. Cryoscopic constant denoted as Kf. Measured in it is measured in degrees Celsius per mole per kilogram. Degrees Celsius per mole per kilogram, because we said depression in freezing point for 1 mole when dissolved in 1,000 grams. And or if you don't say per kilogram, you can say per 1,000 grams. Okay, so but someone could give this cryoscopic constant, this Kf in degrees Celsius per mole per 100 grams of a solvent. It is possible for someone to give Kf per kilogram. That is the standard. But someone can as well give the Kf. Kf is cryoscopic constant. Kf in degrees Celsius per mole per 100 grams. I can make this one better. I can say Kf in degrees Celsius per mole per 100 grams. So here the volume of the solvent is lower. Here the volume of the solvent is higher. Let's look at some few. One of them is water. The known cryoscopic constant per kilogram is 1.86. 1.86. The other one is benzene, is another solvent. Benzene, it is 5.12. Another one is camphor. Camphor is 40. This is 40. And then another one is ethanoic acid. Ethanoic acid, and it is 3.90. Now, remember we said the colligative properties depend on amount of solute dissolved. The depression is going to depend on how much solute has been dissolved. So they are saying that if you dissolved a given solute, whatever the solute, irrespective of its nature, 1 mole of a solute, non-volatile solute, dissolved in water, whose volume is equal to 1,000 kilograms, the depression caused will be 1.86. That's what it means per mole. 1 mole of any solute dissolved in 1,000 grams of water. The depression in freezing point of water will be 1.8. If you got benzene and you dissolve benzene 1,000 grams and you dissolve 1 mole of a non-volatile solute, you will get 5.12 degrees Celsius as the depression in its freezing point. But then there are books that will express that cryoscopic constant per 100 grams. 100 grams is a smaller amount of the solvent. Okay? But we are dissolving the same quantity of the solute, 1 mole. So we expect that since the solute is the same quantity but the solvent is lower, the solute will express itself as being much there. So it will cause a bigger depression in freezing point. So since this solute is smaller 10 times than this one, because this is 1,000, this solvent is 1,000 grams, but this solvent is 100. That is 10 times smaller than this. So the depression will also go up 10 times. Okay? In other words, what I'm saying, that for us to get the depression here in 100 grams should be 1.86. Okay? 1.86 times 1,000 divided by 100, which should give us 18.6 degrees Celsius. In other words, the depression in freezing point is higher for smaller volumes of the solvent. And if the volume of the solvent is 1,000 and it decreases 10 times, the depression in freezing point goes up 10 times. So this one would be 51.2. This one will be 400. And this one will be 39.0 in per mole per 100. This is per mole per kilogram. So these values, when they are given, it's very important you pay attention to the units being used. Now, when we know these constants, then it is very possible for us to proceed and look at the calculations involved, because these constants are easy for us to use. Remember, I've said that these constants mean that this is the depression in freezing point caused when 1 mole of any solute, irrespective of its nature, as long as it's non-volatile, is dissolved in 1,000 grams of water. So we can base on that to make a calculation. So you will find questions, explain. Someone says, explain. Someone says, so someone says that the depression in freezing point of water is 1.6. Is 1.86 degrees Celsius per mole per kilogram. And someone says, explain that. Now, this means that the depression caused by 1 mole of a solute when dissolved in 1,000 grams of water is 1.86 grams. That 1.86 degrees Celsius is depression caused by dissolving 1 mole of a non-volatile solute in 1,000 grams, what is called the 1 kilogram of water. Simple as that. So that is the interpretation of what we call the cryoscopic constant. Now in lesson 3, we are going to see how we use it to calculate molecular mass of non-volatile solute. Chemistry is now going to get intense because now this is the A level chemistry. I want you all to continue viewing our lessons, and please go and view lesson 3 to see how we can look at the calculations and some examples that I'm going to be giving there. So we meet in lesson 3.